Hello everyone. So this video is going to go over another application of partial derivatives. So we saw in class and in another video about how to apply partial derivatives to the idea of utility maximization in the consumer perspective. When a consumer is consuming any two goods, and then how do you understand movements along an indifference curve, and what is the relationship between marginal rate of commodity substitution and marginal utilities, and so on. So this video is going to be an analogous one, but we're going to focus on the production side of things using something called the Isoquant and looking at marginal products. So the first step to get started is to look at a production function. So a production function, when you have two inputs here, so K and L. K is generally capital and L is labor. So a production function in the economic perspective is one that actually relates the transformation of your actual inputs into production, such as capital and labor. It maps the transformation of these inputs into an output that is being produced. So Q here is the output that is produced. K and L are the two inputs used. And we are looking at a very simplistic production function with just two inputs. And just like how a utility function is graphed out using an indifference curve, a production function is going to be graphed out using an isoquant. So iso means equal and quant means just the quantity. So similar to the indifference curve case, just like how every point on an indifference curve gives you the same level of utility, every point on a given isoquant curve will give you the same level of output for a given value of for any combination of K and L, which lies on the isoquant. I'll show you the graph of an isoquant in just a minute. But before we do that, a couple of other quick points to note here. Now, just like in how in the when we looked at utility function where u is a function of x1 and x2, we looked at two interesting expressions, which is dou u by dou x1 and dou u by dou x2. And I said that those are marginal utilities. So here, dou q by dou k is actually called the marginal product of capital, shortly written as NPK. It tells you that if you increase capital or if you change capital by a unit, what's going to be the change in the output, holding labor fixed. So that's the interpretation of that partial derivative. So essentially, if you increase capital by a unit, what's going to be the addition to the output is what the question is asking, is what dou q by dou k measures. Similarly, dou q by dou L measures the marginal product of labor. So at the margin, if you add an extra labor, what's going to be the marginal addition to output? So that's dou q by dou L. Now we'll see in just a moment how these two are actually going to be featured in the isoquant. So right here, what I have is an isoquant map, which is just a series of isoquants. So just like how we did in the indifference curve case, every isoquant will represent a particular level of output, and all points on a given isoquant curve, any combination of K and L on this curve will give you the same level of output. And the higher you move, the greater the level of output. So the output level at IQ2 is greater than that at IQ1, and that's greater than the one at IQ0. Now, notice how just like in indifference curves, the isoquants are also downward sloping. And the trade-off between the two inputs is also going to be very similar here, just like how it was in the indifference curve case. So suppose I'm at a point, just say A. I have a lot of capital. I have a lot of capital here and very little labor. So if I want to get an additional unit of capital and say move 1 unit to the right, maybe to point B, then I'm going to be willing to give up a lot of capital to get to point B. So the slope of the indifference curve is actually pretty steep. The magnitude of the slope is actually pretty high when you move from A to B. On the other hand, when you're at a point, say C, and you want to move to D, you already have enough capital at point C. You already have enough labor there. So to get 1 more unit of labor, you're going to be willing to, and so you have more labor but less capital at point C. So you're going to be willing to give up lesser capital to get 1 additional unit of labor. So the slope here is going to be flatter. So So this, so the slope of the isoquant, actually, when you bring in the calculus notation, the slope is given by dk by dl. And just like how, okay, so for now, I think that is fairly good. Now we'll just use the, right. So there's another interesting element here, which I want to draw your attention to. So just like how we had a term called marginal rate of commodity substitution, to understand the trade-off, how much of one input are you willing to give up to get an extra unit of the other input. So that trade-off is called marginal rate of commodity substitution in the consumer case. So here you have a similar one, which is called the marginal rate of technical substitution. It's technical substitution because you're actually talking about inputs of technology, just so it helps you remember the term. So it shows you for an extra labor unit, how much of capital are you willing to trade off? So that's the interpretation. And MRTS is actually by definition given by the negative of the slope of the indifference curve. So it is minus dk by dl. Just like how we did in the indifference curve case, if you have a production function that's written this way, where Q is a function of K and L, how do you go ahead and find dk by dl? In comes the small increments formula. So we write down the expression or the equation for an isoquant, and then we take the total differential. And given that output across in a particular isoquant is going to be a constant, then once you differentiate that and write out the total differential, d of iq0 will actually be 0. And then once you rearrange the rest of these terms, you are able to actually get an expression for dk by dl. And that appears to be the negative of the ratio of marginal products. And now when you go back to the MRTS, which is the negative of dk by dl, and you plug in the expression for dk by dl, you end up getting that the marginal rate of technical substitution is actually just the ratio of the marginal product of inputs. And this is very similar to how you get MRS to be the ratio of marginal utilities. And something like this is actually going to be visible once you do constrained optimization, which is actually one of the topics that we are studying in this course. So this result will come in to be very useful there. Now, for the rest of this video, I want to go over a few simple problems where we end up computing MRTs. So let's get started. So we're given a particular production function, and this one is actually called the Cobb-Douglas production function. And record these names in your memories because this is going to be frequently showing up. It's often of the form k raised to a particular power alpha multiplied by L raised to a particular power beta, and you may have a constant preceding these two terms. So we are given that A, alpha, and beta are constants, and we want to find MRTS. So MRTS is actually, it was right here. It is just NPL by NPK. And NPL is just dou Q by dou L. NPK is just dou Q by dou K. I'm just going to compute all of this in just one step and put it all together. So dou Q by dou L is going to be, I'll have a beta, I'll have A, K alpha, L to the power beta minus 1. I'm just going to treat K as a constant in that one. And when I do the denominator, dou Q by dou K, I'm now going to have an alpha, and then an A, K alpha minus 1, L beta. Right, so A gets cancelled off, so we have beta by alpha, and this will be K alpha minus alpha plus 1. I'm just moving the K from the denominator up top, and I'm actually just going to move the L from the numerator to the denominator. So we'll have A for beta minus beta plus 1. So you actually end up getting beta by alpha into K by L. And that is your MRTS. And sometimes you may be given specific values of K and L and asked to figure out what MRTS is. Or you may have different values for alpha and beta. I'm just intended to freak you out by giving you very complex numbers like 0.66 and 1.35 and so on. But the principle is the same. And we'll quickly do just one more question here. So we're given a particular production function k square plus 2l squared, and we want to write down the expressions for the marginal products, and hence prove a couple of relationships. So let's get started. So the production function is k square plus 2l square. So let's get dou q by dou k. It's just 2k. Dou q by dou l is 4l. Now, so we've found out these two. Now, if you want to show MRTS, okay, so let's compute MRTS, which is the left-hand side. MRTS is just MPL by MPK. So which is now actually just 4L by 2K. So it is just 2L by K, which actually happens to be RHS. So proved. So that's the first one. In the second, we're asked to prove this particular relationship, K into dou Q by dou K plus L into dou Q by dou L is equal to 2Q. So let's compute this. K into dou Q by dou K is just 2K plus L into dou Q by dou L is actually just 4L. So we get 2K square plus 4L square. Hey, wait, so Q is just K square plus 2L squared. So this is just 2 times K square plus 2L squared. So we have 2Q proved equal to RHS. So that's been proved as well. So in the next video, we'll actually see that this particular expression is a special case of something called homogeneous functions. So we'll discuss that in another video. So I'll see you there.